On the left, a new model called Maple Preview receives the prompt "Make me a carrot cake" on an iPhone and finishes generating its response in about 10 seconds. On the right, receiving the exact same prompt on the same hardware, a different model is still struggling to generate tokens as the timer passes the 6-minute mark. That 10-second completion time translates to 127 tokens per second. Maple achieves this using a 5.31 gigabyte checkpoint, operating at 20.2 billion parameters with 1.49 billion active parameters. The slow model on the right is Bonsai 27B, a post-hoc ternary 1-bit quantization of Quen that was presented to the open-source community just 3 weeks prior as a high-performance option for mobile deployments. We analyze the engineering decisions that make performance leaps like this possible on this channel every week. If you want to understand the architecture behind these models, subscribe below. Seeing a 13-fold speed disparity between two 1-dit models on identical hardware challenges the consensus that bit width alone is the primary lever for mobile performance. The industry standard approach to deploying large networks on edge devices relies on post-hoc quantization. Engineers take a model trained in full precision, usually 16-bit floating point, and mathematically force those weights into lower bit widths to shrink the file size. This animation illustrates the stated goal of that methodology, shrinking the network footprint while maintaining a 90% retention rate of the original model's reasoning quality. Treating full precision quality as the ceiling means the compressed model is mathematically constrained to only ever be a percentage of that original. The architecture was designed for heavy calculation, and retrofitting it for lower precision inherits the structural bottlenecks of the original design. Maple Preview bypasses this constraint through native ternary training. The model is built from scratch at a 1-bit ternary precision. There is no full precision original to compress, meaning there is no original baseline to be a percentage of. By ensuring the precision the model runs at is the exact precision it learned at, DeepGrove successfully eliminates all the architectural compromises that occur when forcing a heavy network into a small, rigid container. Running a 20 billion parameter network directly on a consumer smartphone requires solving a strict thermal and energy equation. The hardware will throttle or shut down if the computational load is too high. The primary roadblock preventing local execution is floating point matrix multiplication. In traditional large language models, this operation consumes the vast majority of the processing power and memory bandwidth. This diagram shows the traditional sequence. The processor must continuously multiply vast grids of detailed fractional numbers against each other to generate a single token, draining the battery and generating heat. DeepGrove's architecture uses 1-bit ternary precision. Instead of detailed fractions, the network's weights are restricted to 3 possible states: -1, 0, or +1. Because multiplying by these numbers is trivial, those heavy matrix multiplications are replaced by simple additions. This swap collapses the total arithmetic workload. The processor no longer executes intensive floating point math. It simply tallies up positive and negative integers. That reduction in workload is the precise mechanism driving the 127 token per second generation speed on mobile hardware. Stripping away the file size of a model is not enough to achieve edge deployment. The base mathematical operation itself must be changed to match the hardware's actual processing constraints. Most architecture searches attempt to optimize for theoretical flops, floating point operations per second. However, theoretical efficiency on paper rarely matches how silicon actually behaves under load. To bridge this gap, DeepGrove placed hardware directly into their training loop. Every proposed architectural configuration was loaded onto and measured by an M4 Mac Mini, capturing actual wall clock inference speed. The search began with a structural configuration of 30 layers and 224 separate expert routing networks. Over multiple iterations, the hardware feedback drove the researchers to a final configuration of 24 layers and 256 experts, deliberately trading away raw model depth for faster execution. Optimizing for wall clock efficiency rather than theoretical math produces a network that responds immediately to the end user, proving that a smaller, faster tool is more usable than a large theoretical model that chokes on mobile silicon. Maple Preview pairs this fast architecture with a 131,072 token context window, allowing users to feed vast amounts of text into a single prompt.
but large context windows create a critical memory bottleneck. Storing the key value pairs, the KV cache, for 130,000 tokens quickly consumes all available mobile RAM, forcing the operating system to kill the application. To prevent memory overflow, DeepGrove implemented hybrid sliding window and global attention. This attention mechanism rigidly bounds the growth of the KV cache, capping its memory footprint regardless of how long the conversation runs. With memory safely capped, the model can utilize its low footprint for direct on-device adaptation.
In a provided experiment, a user mentions a vegan dietary restriction while asking for recipes. That night, the model flags this personal preference and generates a synthetic dataset to retrain its own specific weights. The next day, when adversarially asked to recommend leather bags, the model suggests synthetic alternatives. This overnight dreaming process updates the model in 10 to 20 minutes, while peaking at exactly 5.9 gigabytes of memory utilization. Updating weights directly is more scalable than appending hundreds of personal facts into a text-based system prompt. It keeps the context window clear and the memory footprint low, allowing deep user personalization entirely on local hardware. The developers claim that Maple Preview is the best in its weight class, requires strict scrutiny of the benchmark data. This data table compares the internal evaluations. Looking at the aggregate scores, Maple Preview achieves a 78.7 average, while the larger Qwen 3.5 hits an 82.9 average, beating Maple on 3 of the 4 major tests. DeepGrove's performance claim survives exclusively because they draw a distinct boundary at 20.2 billion total parameters, separating their network from the 35 billion parameter Qwen model. The cost of compressing an architecture down to 1-bit precision becomes highly visible in the GPQA-D benchmark, which tests graduate-level factual knowledge. While Qwen scores an 84.2, Maple Preview drops to 73.5. Maple remains competitive on abstract math and reasoning tests like AIME, meaning the mathematical compression did not damage its logic. Instead, the steep drop in the GPQA-D score suggests the precision loss directly impacts the network's capacity to memorize obscure facts. Native ternary training addresses the mobile inference speed problem, but current extreme low-precision architectures still exact a heavy penalty on a model's ability to operate as a reliable knowledge base. Further limiting these results, every score in the provided table was generated using DeepGrove's internal evaluation harness, rather than independent standardized testing. The researchers used a strict fixed system prompt across all tests that explicitly states, "You are not allowed to use any tools." The authors openly admit that this preview model has undergone minimal post-training for agentic domains, focusing almost entirely on raw reasoning capabilities. If developers attempt to drop this specific checkpoint into a live tool calling loop or an automated agent framework, the reasoning scores likely won't transfer, and the model will fail. Establishing trust in this architecture now relies on the open source community. With the weights available on Hugging Face, independent developers must replicate the 127 token per second generation claim on definitively named iPhone hardware. The ultimate test of the native ternary approach relies on DeepGrove's promised full release, which will incorporate extended reinforcement training. For this architecture to succeed long-term, that extended training must close the specific GPQA-D knowledge gap without slowing down the benchmark inference speed. If reasoning improves, but factual knowledge remains capped in the low 70s, it means building a model natively in 1-bit precision did not eliminate the performance ceiling, it only relocated it from processing speed to factual memorization.